Here are the notes for section 7.6. The title is Normal Distributions, and most of what we're doing comes from this gentleman, and his name is Carl Friedrich Gauss. He was born about the time we signed the Declaration of Independence in this country, and his work was so famous that the German government put a bell curve and the function for a bell curve on their $10 bill. Carl Friedrich was also the gentleman that created the formula for the arithmetic sum, the sum of an arithmetic sequence of numbers, which you may have heard the story about how he found the sum of the numbers 1 plus 2 plus 3 all the way up to 100 very quickly. Most of what we're going to be doing in section 7.6 is learning how to use a bell curve and learning how to convert numbers into areas, and these areas represent probabilities. The first type of bell curve is called a standard normal bell curve. The notation is this: n stands for normal. The first number is the mean, and the second number is the standard deviation. So this is drawn in a picture that looks like this. A normal curve is a bell curve. Mean is at the center, and each step up is 1 because the standard deviation is 1. And we generally draw bell curves plus or minus 3 standard deviations. A z-value represents the number of standard deviations that you are either above or below the mean. So if your z is positive, you're above the mean. If your z is negative, you're below the mean. So the probability that my z-value is less than 3.16 standard deviations below average means that I'm trying to find this area down here. And there's a couple different ways of doing it. You are given a table in the formula page for the AP test. This table has z-scores and areas. So to find the area for 3.16 negative, I'm going to go to negative 3.1 and 0.06. The row contains the ones unit and the tenths unit, and then the column contains the hundredths unit. So z-scores on a table are only rounded to the nearest hundredth or to 2 digits. Anyway, negative 3.16 has underneath it an area, so 0.0008. Z-tables always give you the area from a certain point and below, and since that's what we're looking for, negative 3.16 and below, the area is 0.0008, and it does seem to make sense there. Your calculator contains a z-table. In the distribution menu, you choose normal CDF, cumulative, because we want the area, not PDF, but CDF. You have a left endpoint and a right endpoint. Left endpoint is negative infinity, which is negative 9 times 10 to the 99th. And then we're stopping at negative 3.16, a z-score of negative 3.16. If you do that, your calculator spits out this number, which is in agreement with the table, 0.0008. You're going to have to be able to do the table and the calculator way, because certain calculations later can only be done with the table and not with your calculator. So do the table method, show your work, check on your calculator. Second question: what's the probability a z-score winds up between negative 0.5 and positive 1.21? So again, we're going to find two areas using our z-table. Negative 0.50 has an area of 0.3085, and 1.21 has an area of 0.8869. To find the probability that z is between those two, I'm going to subtract the areas. And the reason is this: z-tables give you the area from a certain point down. So negative 0.5, the area down is 0.3085. I don't want that area. I just want from negative 0.5 to 1.21. So when I find the area for 1.21 and down, 0.8869, that's the area from this line here all the way down. 0.8869 minus 0.3085 gives me the area in between, which is 0.5783. So to get between two values, we're going to be subtracting larger area minus smaller area, because the tables in your calculator give you the cumulative area from a certain point down or to the left. Shortcut or shorter way of doing this is normal CDF from negative 0.5 to 1.21. Left edge, right edge, that area is 0.5783, which again pretty much agrees with the table method. And then finally, to find the area above a certain z value, z greater than 2.5, I'm going to find 2.5 on my z table, 0.9938. That's the area from a certain point down. So here's a z of 2.5. This area here is 0.9938, but that's not what we wanted. We wanted the area above 2.5. So since the entire bell curve has to have an area of 1, to get this area up here, 1 minus 0.9938 gives us 0.0062. The next step in normal curve calculations is to go backwards. You might be given an area and you're supposed to find how many z standard deviations above or below the average that is. So if you want to find the z-score for the smallest 2%, draw a diagram, draw a bell curve, label your z steps. Smallest 2% is somewhere down here. So I'm going to go to my table, and in the middle part, I'm going to look for 0.02. Now the closest I can get is 0.0202, and that corresponds to a row of negative 2.0 and a column of 0.05. So combining those together, negative 2.05, at a z-score of negative 2.05, I have an area of 0.02. Your calculator, again, in distribution has what's called an inverse norm command, and the only thing you need to type in is the area that you're looking for. So if I type in inverse norm with an area of 0.02, I get a z-score out of negative 2.05, which agrees with the table. If I want the middle 95%, I got to do a little bit of thought ahead of time. The middle 95% means that there's 5% left over, 2.5% is down here, and 2.5% is up here. So the area I'm going to look for is 0.025, because I want to know what z-score starts the bottom 2.5%. So going to the middle of my z-table, looking for 0.025. My row is negative 1.9, my column is 0.06. The z value is negative 1.96. Now, because of symmetry, I know that if this is negative 1.96 standard deviations below average, then this would have to be 1.96 standard deviations above average. And this area of 0.025 has to be the same as this area of 0.025. 0.025 plus 0.025 is 0.05, which means the middle part is 0.95, which is what we were looking for. So again, checking that inverse norm of 0.025, if I give you an area of 0.025, what's the z-score? Negative 1.96. If I give you an area of 0.975, which again, from this point all the way down is 0.95 plus 0.025, 0.975 is the area from that point down. That z-score is 1.96, but we found this just by using the symmetry part of a z-table. And finally, what happens if I want to be in the top 5%? Top 5% means that there's 95% below it. Top 5% means you're in the 95th percentile. This is the number we're going to look for in our table. 0.95 doesn't appear exactly. The two closest numbers are 0.9495 and 0.9505. Since 0.95 is exactly in between those two, we're going to use exactly in between these two numbers here. 1.6, and then halfway between 0.04 and 0.05 is 1.645. So that's one of the few z numbers that actually go to 3 digits. In a picture, if I'm looking for the top 5%, I'm looking for an area of 5% here, which means I'm looking for a percentile of 0.95. Inverse norm of 0.95 is 1.64485, which is really close to 1.645. Final calculations leave the world of z-scores and move into more realistic situations. Lots of things are distributed normally, and so this is used in quite a lot of industries. The example we're going to look at is adult U.S. women have heights that are approximately normally distributed with a mean of 65.5 and a standard deviation of 2.5. The reason why that would be important is imagine that you are in charge of purchasing clothes, maybe for adults, and you want to know exactly what proportion of people would be in the small size range or the medium size range or the large size range. Anyway, take the mean, take the standard deviation, draw a bell curve, and put those numbers on there. Mean goes in the middle, 65.5, and then you're going to add on 2.5 3 times to get these 3 values. And then you're going to subtract 2.5 3 times to get these 3 values. So you know that if women have heights normally distributed with a mean of 65.5 inches and a standard deviation of 2.5 inches, then pretty much all women are going to be between 58 inches and 73 inches. Not 100%, but 99.7% approximately are between those heights. So to answer the question, what proportion are less than 62 inches? I'm going to convert 62 inches into a z-score. The z formula, which we learned a long time ago, but here's it again. Take the value that you're interested in, compare it to the mean, and divide it by the standard deviations. So 62 minus 65.5 divided by 2.5 is negative 1.4. A woman that's 62 inches tall is about 1.4 standard deviations below average. How do I convert that into an area or a probability? I go to my table and look up negative 1.400, and I get 0.0808. That area is 0.0808. That means that about 8% of women are less than 62 inches tall. Again, the calculator way, normal CDF from negative infinity up to negative 1.4 is 0.0808 z-scores. Or you could have it calculate this directly by typing in 4 arguments: beginning, ending, mean, standard deviation. So what's the proportion under a bell curve from negative infinity up to 62 inches on a bell curve that's centered around 65.5 inches with a standard deviation of 2.5? If you type that in you'll get this. You should be familiar with getting the answer all three of these ways. So again, do the table way first, draw your diagram, check with your calculator, and then do it this way as well. So the last two examples are pretty much the same thing. I'm going to just go through them quickly and you can copy them down. Between 65 and 70 inches is going to be 2 z-scores. I'm looking for the area between this z-score and this z-score. So I go to my table twice. This is a percentile. This is a percentile. To get the area between those two, take the larger percentile and subtract the smaller percentile. 9641 minus 4207 is 5434. And you can check with the two commands from negative 0.2 to 1.8 in z-scores, or from 65 to 70 on a bell curve centered around 65.5 and standard deviation of 2.5. All of this work is required. You must have a well-labeled diagram. You must have both scales labeled X and Z, and you're going to be actually adding a lot more onto these bell curves, so make them nice and big because we're starting to get some habits that'll be used when we tackle inference, which is the last part of the class. And then finally, above 72 inches, a z-score of 2.6. The percentile is 99.53. So if you're above 72 inches, you're in the 99.5th percentile, but they want to know what percent are above that. So I'm going to take that 0.9953 and subtract it from 1 and get 0.0047. So above 72 inches is less than 5% of, less than 0.5% of all women. Again, diagram, I was only working up here, so it's okay to label half of this. Just make sure you have X and Z on there, and then use your calculator, z-scores, or height to positive infinity, mean, and standard deviation. Okay, that's it. You'll get more practice in class.